Hi, well, I'm Stephen Escherba, and I'm here to tell you a little bit about the Arrhenius view of catalysis. So the idea I'm just going to develop here as a kind of an abstract way with just A and B. We're thinking A and B produce some compound AB, and that's uncatalyzed and it's slow, let's say, and I've kind of depicted it as if it were a one-step reaction with this great big energy of activation, and the big energy of activation is what tells you that it's a slow reaction. On the other hand, we could imagine that there's some catalyzed reaction, which I've kind of indicated in a generalized way, by putting that X up there. X is the catalyst, and so this is a catalyzed reaction, and it's fast. Now, when you're thinking about a catalyzed reaction, generally you have in mind some underlying mechanism that makes it fast. So in this case, the mechanism that I'm thinking about goes something like this. A meets X, okay, and produces this reaction intermediate AX, and then AX itself gets consumed by reacting with B, and what happens there is it makes an AB compound and regenerates X. So you can see that X must be a catalyst in this reaction, and AX must be a reaction intermediate. Now, why would this be fast? Well, it's obviously a two-step reaction, but what if it happened that the two-step reaction produced something like this, okay, in which now the net energy of activation is much smaller than it was before it was catalyzed. Well, a smaller energy of activation will make the reaction go faster. And we could do one more little thing here, which is that we're noticing that this reaction intermediate, AX, appears after the first step. So that must be AX that appears right there. And we would also probably want to update our reaction profile here to say we're starting off with AB, it's true, but we would add X to the mix here, and then of course, because it's catalyzed and X is the catalyst, it would be regenerated at the end. Okay.